So I have in the calculator a set of data. And what we're going to explore today is what we do in a situation when we create a scatter plot and we notice that it doesn't look linear. Okay? In the prior chapter, in the prior lessons, everything we looked at, we said, hey, this data is either linear or it's not. And almost all the examples I gave you, the data turned out to be linear. So we didn't have to worry about what happens if it's not linear. So today we'll finally start to worry about that. What happens when you graph your data and it's nonlinear? In list 1, I have the depth of water in meters. This is in a lake maybe or somewhere. And depth 2 is the intensity of light at that depth, measured in a unit called lumens. Lumens is a unit of light intensity. So something with a lot of lumens, like 168 lumens, would be brighter than something that had, like maybe at 8 meters, only 61.87 lumens of light intensity. Okay? All right, so let's take a minute to graph this and see what happens. So we're going to go to second y equals. Plot 1, list 2 looks good. All right, I'm going to press zoom 9, and we get this picture. Okay. You can still talk about direction of this relationship, right? Is it positively or negatively associated? Well, as x gets bigger, y seems to be getting smaller. This is negatively associated. The next question to ask about is form. Is it linear or not? Well, I would say this one is not linear, okay? And you can kind of tell why that's going to be the case, because if you look at this picture here, and you tried, even if you just tried to draw in a line of best fit, there's what it would look like. You can see already that there'd be a pattern in your residuals. Look at your residuals here. Here, that residual is positive. Maybe that's 0 or negative. This residual is negative, 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 comes back to 0 and is back to positive again. So your residuals, those blue lines, okay, have a distinct curve pattern. And we discussed already that when your residuals have a pattern, that means that probably a line is not the best model for the data. Okay. So what do? Well, we do know how to do one thing. We know how to do linear regressions. And we know how to do them in the calculator pressing stat 8. Right? Stat, calculate, number 8, in linear regression. The problem is I don't think my data is linear. So what I'd like to do is figure out a way to linearize the data. This is a very common technique in statistics. You take your data and you say, all right, how could I transform it so it becomes linear? One trick or one procedure you could do to try and linearize data is to start by trying the following. Go to Stat Edit and go to List 3. And in List 3, I'm going to take the log of List 2, the log of my y values. Now, we'll do other kinds of transformations in the future, but today we're just going to focus on this one. Okay, we hit enter, and we get this list of numbers. Okay. So the next thing we're going to do is we're going to create a scatter plot now between list 1 and list 3. And what we're hoping that this scatter plot looks linear. And the reason I'm hoping for that is because if it does look linear, then I'll be able to do a linear regression. So I'm going to do second 3, make that list 3. Okay. Let's try zoom 9 now. So we're doing list 1 versus list 3, or we're doing x versus the log of y. Zoom 9. Oh, wow. Now that is pretty. That definitely looks linear. All right, so I claim that we're happy that this data looks linear. You can see if you look at this graph that a line of best fit goes through here pretty nicely. It looks like it's not going to miss too many of the points, or the residual is going to be very small. All right, let's take a look at how well this line of best fit does. So I'm going to go back to the calculator. I'm going to go stat, calculate, number 8, which is linear regression. I got to be careful. I'm going to do x, which is in L1, comma, y, which is in L3. I should say log y, actually. Right? I'm not going to bother sticking this into y1. I'm not going to worry about that. Hit enter, and here's our output. Wow. That is the strongest correlation that we've seen in any of these videos so far, right? The line fits this data extremely well. So the next question would be, is the line appropriate for this data? how do we check something like that? All right, so it would be nice if we just checked the residuals. I mean, this r being so high here, or so close to -1, really tells me that the line's going to work well here. This thing's almost a perfect relationship. We could check the residuals if we want. Let's just do that real quick to review it. I'm going to do second stat plot. I'm going to go to that first stat plot. I'm going to go down to that y list. And I'm going to do second stat to get my residuals, which are usually number 7 on the list. Okay, there they are. Zoom 9. And my residuals have a nice scattered pattern. I'm pretty happy about that. So that means that since our residuals are scattered, that this line of best fit fits the data well. Okay, so let's go back and take a look at this and write down our line of best fit. So here we go. Now you better be careful here. This is the log of y hat. It's not y hat. Equals 2.948 minus 0.145x. Okay. All right, so now we have a line of best fit for the transformed data of x versus log y. We're very happy with this line. We're convinced it models the data well. There's only one problem. Or I shouldn't say problem, but one thing I desire. I would like to have an equation that just had y in it. Not log y. I'd like to just be y equals. So we're going to do something called perform an inverse transformation. Okay. So what's an inverse transformation? An inverse transformation is a way to take something like this that has log y hat in it and get rid of that log. I'd like to get rid of that. Okay? So before I can do that, I need to remind you of something from your mathematical past. All right, so first off, quick question I want to ask you is, if I write log 100, do you remember what that means? First off, when you see a log and there's no number as a base, you'd assume there's a little 10 down here, right? And this means what power do I put on 10, this 10, to get this number? What power do I put on 10 to get 100? And the answer is 2. Okay? So now I'm going to write something that's going to seem strange at first, and then maybe you'll see where I'm heading with it. Suppose I write 10 to the log 2, log 100 power. There we go. Take a look at that. I'm saying I want 10 and to this whole log expression as an exponent. But you know what that is. Log 100 is 2. So this is 10 squared, and then that gives you back 100. Notice something. Okay. All right, so here we go. Now you got to pay attention. You might have to pause for a minute after you watch this next part, because you might be a little unsure. Ready? Okay. Now, log 7, I'm not sure anybody knows what that is without getting a calculator out. That's saying, what power do I put on 10 to get 7? That's what log 7 is asking. Okay, so log 7 is equal to the power I put on 10 to get 7. That's what log 7 equals. Now, I am going to emphasize the fact again that I don't know what that number is, and I claim it doesn't matter, because I am doing 10 to the power that I put on 10 to get 7. By definition, I have to get 7 as an answer. So in summary, what you know is if you have 10 to the log x power, the answer would just be x. There's only one restriction here. X has to be greater than 0. We just have to require that. Okay? You can't take the log of negative numbers or 0. All right? But this is a true fact. So we're going to take this fact and we're going to use it to get our line at best fit to just be y equals. I don't want it to be log y hat anymore. So here's my line at best fit here. I'm going to take this to a new page and we're going to work on it now. So like I said, actually, I don't want that log y hat anymore. So I know that if I do 10 to that power, I'm just going to get y hat. Finally I have an equation that says y equals. That's what I wanted. Now you better be careful. You can't just do 10 to the log y hat power without doing 10 to this whole power. Okay? So that's what we get. All right. So I'm going to write this like the following. I'm going to say 10 to the 2.948 plus negative 0.145x. That's my exponent. Okay, so what I have now is an equation that just says y and x in it, but I'm going to work on it a little bit more. I want to change it a little bit more, so I want to ask you another question you may not remember. At some point in the past, you learned how to do things like this, x to the a times x to the b. And you learned that when you have the same bases, you can just add the exponents when you're multiplying. And most of your mathematical life, you went in this direction. You went from the thing that's on the left here to the thing that's on the right. But you've always had the ability to go backwards. It's an equal sign. You can go either direction. Okay, ready? So we're going to use this idea on that side of the equation. Watch what happens. Y hat equals 10 to the 2.948 power times 10 to the negative 0.145 times x power. Okay. We're getting there. One more thing I want to remind you of for your mathematical past. You also learned this about exponents. If you had x to the a to the b power, you knew you could multiply those exponents. And you've always gone this direction, but you've always had the ability to go backwards. So I'm going to take that idea, this idea right here, I'm going to apply it to that situation and watch what we get. Y hat equals 10 to the 2.948 times 10 to the negative 0.145 to the x. Okay. We're just about there. I'm hoping you're looking at this equation now and saying, hey, wait a minute. That looks like something of this form, y equals a times b to the x. That's what this looks like, where this number is a and that number is b. So the last thing I'm going to do here is I have these expressions like 10 to the 2.948 power right here, and I got 10 to the negative 0.145. Let's finish off by typing those into our calculator to get actual numbers. Because if I do that, it's really going to look just like y equals a times b to the x. So 10 to the 2.948 power equals, 887.156. And then 10 to the negative 0.145 equals 0.716. And what you notice is that it's exactly an exponential equation. Okay? Now, notice the variables here are y and x. So this means that this is a really good model for our original data. So let's go back to the calculator, and we're going to do one more thing to finish off. So here we go. We're going to go y equals. I'm going to type that equation in. 887.516 times 0.716 to the x power. Now, remember, this is supposed to model the original data, not the residuals, not log y versus x. It doesn't model that. This is x versus y. So we're going to go back to our stat plot now, and we're going to turn it back to the original data. So our x list is definitely L1. Our y list, second L2. There you go. Now you can press zoom 9 and be awed. Wow. We have found the perfect model for our original data. And it's an exponential model.